NASA is on alert. An asteroid designated 2024 RW1 is on a collision course with the Moon. Impact calculations show a direct hit in December 2032, and for the first time in human history, we're watching a confirmed celestial impact years before it happens. Right now, this 40-meter space rock is traveling at 61,000 kilometers per hour toward our lunar companion. And unlike near-Earth asteroids that narrowly miss us, this one has zero chance of deflection. The Moon will be hit. The impact energy is calculated at 15 megatons. That's roughly 1,000 times more powerful than the Hiroshima atomic bomb, concentrated into a single point on the lunar surface. The impact site has been narrowed down to a 50-kilometer zone near the Oceanus Procellarum region. Computer models predict the collision will create a fresh crater between 800 meters and 1.2 kilometers in diameter. Amateur astronomers will be able to witness the flash from Earth with nothing more than a backyard telescope. The probability of this scenario playing out exactly as predicted is 99.7%. Dr. Richard Binzel from MIT stated in November 2024 that this represents the first time humanity has had multi-year advance warning of an extraterrestrial impact on any celestial body in our immediate vicinity. Even more significant, NASA updated the object's orbital status to definite impact just 3 weeks ago, upgrading it from probable collision after refinement of trajectory data from 5 different observatories. 2024 RW1 has broken the pattern we thought governed near-lunar approaches. Most objects this size either collide within weeks of discovery or miss entirely. Here's what should concern you most: the debris field. Computer simulations show that material ejected from the impact will reach altitudes of up to 100 kilometers above the lunar surface, and some of it won't fall back down. Think about that. Before we dive deeper into what this impact means for lunar science and future exploration, if you want to stay updated on what could be the most observed celestial collision in human history, don't forget to hit that subscribe button and turn on notifications, because what we're about to reveal will change how we think about lunar impacts and planetary defense. And leave a comment telling us, should NASA attempt to deflect this asteroid even though it's not heading for Earth? Let's talk about how this asteroid was discovered. 2024 RW1 was first detected on September 3, 2024, by the Asteroid Terrestrial Impact Last Alert System in Hawaii. Initial orbital calculations suggested a near-miss scenario with the Moon. The detection itself was almost missed. The asteroid appeared on only 3 frames captured over a 2-hour observation window before clouds rolled in and ended the session. But here's where it gets really strange. As more observational data came in over the following 6 weeks, the trajectory didn't behave like typical near-lunar flybys. Every refinement of the orbit brought the predicted closest approach point closer to the lunar surface, not farther away as is statistically more common. The team at the Minor Planet Center in Cambridge, Massachusetts, initially flagged the calculations as potentially erroneous. Objects don't normally show this pattern of converging probability. Usually, as more data comes in, the uncertainty ellipse either expands or shifts, but the central prediction remains relatively stable. With 2024 RW1, every new observation made the impact more certain, not less. By the time 50 observations had been recorded from 6 different observatories across 3 continents, the mathematical probability of lunar impact had climbed from 3% to 78%. By October 18, 2024, the European Space Agency's Near-Earth Object Coordination Center ran their own independent calculations using completely different software and observation data sets. They confirmed what NASA's Jet Propulsion Laboratory had been seeing. This wasn't a flyby anymore. The Moon's gravity well was going to capture this object in the worst possible way. For context, the Moon gets hit by space debris constantly. An estimated 180 impacts of objects larger than 10 centimeters occur every year. But those are random, untracked, and discovered only after the fact when new craters appear in lunar imaging. Between 2005 and 2024, NASA's Lunar Reconnaissance Orbiter identified over 47,000 new impact craters that weren't present in earlier surveys. This is different. We know it's coming, we know when, We know approximately where, and we have years to prepare instruments and position spacecraft to observe it. The asteroid completes one orbit around the Sun every 1.4 years. Its orbital path crosses Earth-Moon space twice per cycle. The December 2032 approach represents the 7th time this object will pass through our neighborhood since its discovery. Each previous approach has been documented and measured, allowing astronomers to refine the orbital model with increasing precision. But the mysteries don't stop there. Spectroscopic analysis of 2024 RW1 shows a composition consistent with S-type asteroids, silicate materials with some nickel-iron content. That's normal for near-Earth asteroids. Approximately 17% of all near-Earth objects fall into this classification. What isn't normal is the albedo reading. The object reflects only 7% of the sunlight that hits it, making it exceptionally dark even for its classification. Most S-type asteroids reflect between 10 and 22% of incident light. An albedo of 7% places 2024 RW1 at the extreme low end of the distribution, suggesting either an unusual surface composition or a layer of space-weathered material much thicker than expected for an object of this size and presumed age. This suggests the surface has been exposed to the space environment for an extended period, possibly hundreds of millions of years longer than typical objects in similar orbits. Or it could indicate the presence of organic compounds, which tend to darken surfaces. Without a sample return mission, distinguishing between these possibilities remains speculative. Dr. Marina Brozovic from NASA's Jet Propulsion Laboratory mentioned in an October 2024 briefing that the radar observations showed an irregular shape with a length-to-width ratio of approximately 2.4 to 1. This makes it elongated, possibly indicating this is a contact binary, two smaller asteroids that gently collided and stuck together millions of years ago. If that's true, the impact dynamics become far more complicated. A contact binary doesn't hit a surface like a solid rock. The structural weakness at the contact point means the object can fragment on approach or upon initial contact with the lunar surface, creating multiple simultaneous impact sites instead of one clean crater. Laboratory experiments conducted at NASA's Ames Research Center using scaled models suggest that contact binaries impacting at angles shallower than 30 degrees have an 80% chance of separating into component pieces before the primary impact. Each piece then creates its own crater, resulting in a distinctive pattern of overlapping or closely spaced impact features. Planetary defense simulations for Earth impacts account for this possibility. The Chelyabinsk meteor that exploded over Russia in 2013 is thought to have been a weakly bound rubble pile that came apart in the atmosphere. But no one has modeled a contact binary impact on an airless body with the moon's specific gravity and surface composition with high fidelity. Here's where it gets really weird. The object's rotation period was measured at 4.7 hours during initial observations in September 2024. This was determined through brightness variations as the asteroid tumbled through space, presenting different surface areas to observers. By December 2024, follow-up observations from the Arecibo Observatory and the Goldstone Deep Space Communications Complex showed the rotation had slowed to 5.1 hours. That's a measurable change in just 3 months. A 0.4-hour change in rotation period for an object this size requires a significant torque. Objects this size in stable orbits don't spontaneously change their rotation rates without a reason. The rotational energy has to go somewhere or come from somewhere. Either the object experienced an outgassing event that created asymmetric thrust, like a comet developing jets as subsurface ice vaporizes, or there's internal structural shifting happening as tidal forces from Earth and Moon repeatedly stress the object during close approaches. Each time 2024 RW1 passes within a few 100,000 kilometers of Earth or Moon, tidal forces stretch and compress the asteroid slightly, potentially causing internal fractures to propagate or rubble pile components to shift position. A third possibility, though less likely, is that the asteroid collided with a much smaller object during the observation gap, transferring angular momentum and altering the spin rate. Given the density of small debris in near-Earth space, this isn't impossible, but the odds of detecting such a collision's effects without witnessing the collision itself are extremely low. And then something that shouldn't be possible happened. During a particularly close Earth flyby in March 2025, ground-based radar detected what appeared to be a brief increase in radar cross-section, suggesting the object temporarily became larger or changed shape. The increase lasted approximately 40 minutes and amounted to a 15% expansion of the measured cross-section. The data was reviewed by 3 independent teams at NASA's Jet Propulsion Laboratory, the European Space Agency's Space Situational Awareness Center, and the Planetary Defense Coordination Office. All confirmed the anomaly. All verified the calibration of the radar systems. No one can fully explain it. One hypothesis suggests that thermal expansion from sudden solar heating caused surface materials to fracture and create a temporary halo of dust and small particles around the asteroid, increasing the effective radar cross-section without actually changing the solid body's dimensions. But thermal expansion sufficient to cause visible fracturing should also produce detectable outgassing, and no spectroscopic evidence of gas emission was observed during that period. Another possibility is that the asteroid has a bimodal structure, with a dense core and a loosely attached outer layer that can shift position under tidal stress, temporarily changing the overall shape. This would be consistent with the contact binary hypothesis, but it raises questions about how such a structure remains stable over millions of years of orbital evolution. But there's another problem that no one is talking about. The impact trajectory brings 2024 RW1 in at a relatively shallow angle, approximately 15 degrees from horizontal. This isn't a vertical plunge like most impact scenarios modeled in laboratory experiments and computer simulations. Most impact modeling assumes angles between 45 and 90 degrees, because these represent the statistically most common impact geometries. Shallow angle impacts are far more efficient at excavating material and creating asymmetric ejecta patterns. Think of skipping a stone across water versus dropping it straight down. The physics is dramatically different. A vertical impact creates a circular crater with ejecta distributed relatively evenly in all directions. A shallow impact creates an elliptical crater with the majority of ejected material concentrated in a cone extending downrange from the impact point. Early models suggest ejecta could be scattered across an area 200 kilometers wide and 800 kilometers long, potentially damaging or contaminating multiple sites of scientific interest, including regions being considered for future Artemis mission landing sites. The South Pole region, which contains permanently shadowed craters believed to harbor water ice, lies approximately 2,400 kilometers from the predicted impact site. Under normal circumstances, this would be considered a safe distance, but computer simulations of shallow-angle impacts show that the largest ejecta fragments, those exceeding 1 meter in diameter, can travel ballistic trajectories extending thousands of kilometers. A 2-meter boulder ejected at 2 kilometers per second at a 30-degree angle will travel over 3,000 kilometers before impacting the surface again. If the impact ejects even a dozen such boulders in the direction of the South Pole, it creates a contamination risk for ice deposits and future landing sites. NASA's Lunar Reconnaissance Orbiter has been repositioned to ensure its orbital path will allow real-time observation of the impact from a safe distance of at least 500 kilometers. The spacecraft carries instruments capable of detecting the impact flash in multiple wavelengths, measuring the temperature of the briefly molten crater floor through infrared sensors, and analyzing the composition of ejected material through spectrometry as it passes through the debris plume. The Lunar Reconnaissance Orbiter camera, which has a resolution of 50 centimeters per pixel in its highest resolution mode, will attempt to image the crater within hours of formation, while the ejecta pattern is still pristine and before subsequent micrometeorite bombardment begins to degrade the features. But here's the concern that keeps mission planners awake at night. What if debris reaches orbital velocity? The escape velocity from the lunar surface is 2.38 kilometers per second. That's significantly lower than Earth's 11.2 kilometers per second, which means it's much easier for impact ejecta to achieve orbit or escape the moon entirely. Computer simulations of the 2024 RW1 impact, based on the known impact velocity, angle, and estimated object density, show that approximately 0.2% of the ejected material will be launched with velocities between 2.38 and 3.5 kilometers per second. That translates to between 500 and 2,000 individual fragments, ranging from pebble size to boulder size, each one a potential hazard to any spacecraft operating in lunar orbit. These fragments won't remain in stable orbits. Most will re-impact the lunar surface within days to weeks. But during that window, they represent a genuine collision risk. The debris would gradually deorbit over weeks to months due to perturbations from Earth's gravity and the slight gravitational anomalies in the moon's mass distribution. But during that window, the risk to missions increases substantially. A 10-centimeter fragment traveling at orbital velocity carries enough kinetic energy to catastrophically damage or destroy a spacecraft. And December 2032 happens to fall within a planned Artemis crew rotation period. Current mission architecture calls for a crewed Orion spacecraft to be in lunar orbit for up to 30 days during each mission, serving as a base for surface operations and crew transfers. If a mission is underway when the impact occurs, mission controllers will face difficult decisions about risk tolerance. Dr. Jacob Bleacher, NASA's chief exploration scientist, stated in a November 2024 presentation that mission timelines might need adjustment depending on refined impact predictions and debris field modeling. The agency is developing protocols for debris avoidance maneuvers and considering whether to require all spacecraft to depart lunar orbit at least 48 hours before the predicted impact time. The impact site itself presents a unique scientific opportunity that hasn't existed since the Apollo missions deliberately crashed spent rocket stages into the moon to create seismic data for study. Those controlled impacts, part of the Apollo passive seismic experiment, revealed crucial information about the moon's internal structure. The seismometers detected moonquakes and reverberations that traveled through the lunar interior, allowing scientists to map the thickness of the crust and detect the presence of a small metallic core. This will be a natural impact with known parameters: incoming velocity of 61,000 kilometers per hour, impact angle of 15 degrees, object size of approximately 40 meters, and approximate composition of silicate rock with nickel iron content. Those parameters allow for predictive modeling with unprecedented accuracy. Seismometers left on the lunar surface by future missions could detect moonquakes triggered by the impact, revealing information about the moon's internal structure in that region. The impact will generate seismic waves that propagate through the lunar crust and mantle. By measuring the arrival times and characteristics of these waves at multiple locations, scientists can refine models of lunar interior structure. The impact crater will excavate material from beneath the lunar regolith, exposing fresh rock that hasn't been weathered by billions of years of micrometeorite bombardment and solar wind. The regolith layer in the Oceanus Procellarum region is estimated to be between 8 and 12 meters deep. An impact of this magnitude will penetrate well beyond that depth, potentially reaching the underlying basalt bedrock and exposing material that last saw sunlight 3 billion years ago when volcanic activity was still shaping the lunar surface. But acquiring that data requires getting instruments there before December 2032. Multiple commercial lunar missions and international space agencies have expressed interest in landing payloads near the predicted impact zone, specifically to study this event. Companies including Asteroid, Intuitive Machines, and iSpace have all indicated interest in bidding on instrument delivery contracts if NASA or other agencies issue requests for proposals. Here's where things get complicated. The impact will occur during lunar night at the impact site. Each lunar day lasts approximately 29.5 Earth days, meaning 2 weeks of continuous sunlight, followed by 2 weeks of continuous darkness. The December 2032 impact timing places it roughly 8 days into the lunar night at the Oceanus Procellarum impact site. The flash will be visible from Earth, but surface-based instruments at the impact location will be operating in minus 173 degrees Celsius darkness without solar power. Electronics that function perfectly at room temperature become brittle and unreliable at these extreme temperatures. Batteries lose capacity. Moving parts seize. Any mission sent to study the impact from the surface will need to either arrive during lunar day and survive 2 weeks of night, or land immediately after the impact and operate on battery power long enough to collect critical data before systems freeze. Surviving lunar night requires either radioisotope heating units, which are expensive and require special nuclear regulatory approval, or extremely well-insulated battery systems capable of maintaining minimum operating temperatures for extended periods. The Japan Aerospace Exploration Agency has proposed a small lander mission specifically designed for this scenario. The spacecraft would arrive at the Moon 1 month before impact, land 200 kilometers from the predicted impact site in a location that will be in sunlight during the impact, and deploy a network of seismometers and high-speed cameras capable of detecting both the acoustic shock transmitted through the lunar surface and the visual flash of the impact itself. If successful, it would be the first time we've ever recorded the sound, or rather the vibration, of a natural impact on another world. The Moon has no atmosphere, so there's no sound propagation through air, but seismic vibrations travel through solid rock, and sufficiently sensitive instruments can detect these vibrations as the equivalent of sound waves traveling through the lunar crust. The proposed instruments would sample at rates exceeding 10,000 times per second, allowing reconstruction of the impact acoustic signature with high fidelity. This data would provide insights into the mechanical properties of the lunar subsurface that are difficult to obtain through any other means. But let's talk about what this means for planetary defense. 2024 RW1 isn't hitting Earth, so there's no immediate threat to humanity. But it's forcing us to confront an uncomfortable question. What if it was? The detection came 8 years before impact. That's actually a decent warning window by current standards. Most impact warning scenarios discussed in planetary defense circles assume detection times ranging from a few weeks to a few years before collision. 8 years would be considered a best-case scenario for a detected threat. The issue is what you do with that warning. If this asteroid were Earth-bound instead of Moon-bound, 8 years would theoretically be enough time to mount a deflection mission, but theoretically carries a lot of uncertainty. The DART mission in 2022 successfully demonstrated kinetic impactor technology by changing the orbit of asteroid Dimorphos. That mission required 4 years from approval to impact, and that was with an enormous amount of preparation work done beforehand during the mission design phase. The target asteroid had been selected years earlier. Its orbit was well characterized, and the mission profile had been studied in detail long before construction began. A real planetary defense scenario would require detection, confirmation, trajectory refinement, mission design, spacecraft construction, launch window calculation, and interception, all within the available warning window. 8 years starts to look much tighter when you account for bureaucratic approval processes, international coordination, funding allocation, and the realities of spacecraft manufacturing schedules. Designing a spacecraft from scratch typically requires 3 to 5 years. Manufacturing and testing add another 1 to 2 years. Launch window constraints might add months of delay if the ideal departure date is missed. And all of this assumes immediate approval and unlimited funding, neither of which is realistic for any government space program. And here's the problem with 2024 RW1 specifically. It's small enough to be difficult to deflect, but large enough to cause regional devastation if it hit Earth instead of the Moon. The 15 megaton impact energy would flatten everything within a 15-kilometer radius if it struck a populated area. The 1908 Tunguska event in Siberia, which flattened 2,000 square kilometers of forest, is estimated to have been caused by an object between 50 and 100 meters in diameter. 2024 RW1 at 40 meters sits just below that range, but would still cause immense destruction. Dr. Lindley Johnson, NASA's former planetary defense officer, mentioned in a 2023 interview that objects in the 30 to 50 meter size range represent a particular challenge for planetary defense because they're small enough to be numerous and difficult to track comprehensively, but large enough to cause significant damage. These are the objects that can slip through current survey programs and appear with little warning. Current surveys have identified approximately 40% of near-Earth asteroids larger than 140 meters. The goal established by the United States Congress in 2005 was to find 90% of all near-Earth objects larger than 140 meters by 2020. That goal has not been met, though significant progress has been made with roughly 10,500 near-Earth asteroids now cataloged. But for objects in the 2024 RW1 size range, we've probably only found 10 to 15% of the total population. Estimates suggest there are between 300,000 and 500,000 near-Earth asteroids larger than 30 meters. We've found approximately 40,000 of them. That means hundreds of thousands of potential impactors are out there, untracked and uncharted. Most will never threaten Earth. Their orbits don't intersect Earth's path, or they do so only at times when Earth is elsewhere in its orbit. But we won't know which ones do threaten us until they're already dangerously close, possibly too close for effective deflection. The average warning time for asteroids in the 30 to 50 meter range, based on historical discovery circumstances, is approximately 3 weeks. That's nowhere near enough time to mount a deflection mission. It's barely enough time to evacuate a predicted impact zone if the location can be determined with sufficient precision. Now let's consider the visibility of the impact from Earth. Amateur astronomers with 8-inch telescopes and basic cameras should be able to capture the impact flash, assuming clear weather and proper positioning. The impact will last only a fraction of a second, but the thermal signature will be intense enough to register across multiple wavelengths. At the moment of impact, temperatures at the impact site will briefly exceed 5,000 degrees Celsius, hot enough to vaporize rock and create a plasma plume that will glow brightly in visible light and infrared. Professional observatories are already planning coordinated observation campaigns. The goal is to have at least 20 different instruments pointed at the impact site from locations distributed across Earth's surface, ensuring that weather or technical failures at one site don't result in missing the event entirely. Coordination is being managed through the International Astronomical Union's Minor Planet Center, which is serving as a clearinghouse for observation plans and data-sharing agreements. The Hubble Space Telescope will be positioned to observe the impact if orbital mechanics and scheduling allow. Hubble orbits Earth every 95 minutes, meaning its ability to observe any specific target depends on whether that target is visible during orbital night, when the telescope can point away from Earth without sunlight interference. Mission planners are calculating whether the December 2032 impact timing will align with a favorable Hubble orbit. The James Webb Space Telescope's infrared sensitivity makes it ideal for detecting the heat signature of the briefly molten impact crater, but its observing schedule is allocated years in advance through a competitive proposal process, and securing time for this event required significant justification. Webb's mid-infrared instrument can detect temperature variations of less than 1 degree at lunar distances, making it capable of imaging the cooling crater floor for hours after impact. Multiple military early warning satellites designed to detect missile launches have infrared sensors sensitive enough to detect the impact from Earth orbit. The Defense Support Program satellites and their successors in the space-based infrared system are designed to detect the infrared signature of rocket plumes against the cold background of space. An asteroid impact produces a far more intense thermal signature than any missile launch, making detection essentially guaranteed if any satellite has a line of sight to the impact location. While the data from these platforms is typically classified, there's precedent for declassification and release to the scientific community for events of major scientific interest. The Chelyabinsk meteor explosion in 2013 was detected by U.S. military satellites, and the data was subsequently released, allowing scientists to reconstruct the event in detail. The impact will also be observable by spacecraft currently in lunar orbit or future missions arriving before 2032. China's Chang'e program has maintained continuous presence in lunar orbit since 2019, with multiple orbiters and relay satellites. India's Chandrayaan program includes plans for additional lunar missions in the late 2020s. And commercial lunar orbiters from companies like Intuitive Machines and Astrobotic represent potential observation platforms if they remain operational through 2032. This will be the most comprehensively observed natural impact in history, and the data will be invaluable for validating impact models, understanding crater formation processes, and refining our understanding of how impacts shape planetary surfaces. But here's what makes this genuinely concerning: the debris analysis. When material is ejected from an impact crater, it doesn't just fly away and disappear. The physics of impact cratering dictates that ejecta follows specific patterns based on the impact energy, angle, and target material properties. Some ejected material achieves escape velocity and leaves the moon entirely, entering heliocentric orbit around the sun. Some enters temporary lunar orbit before eventually crashing back down, either immediately or after multiple orbits. And some follows ballistic trajectories, creating secondary impacts hundreds of kilometers away from the primary crater. Material ejected with enough velocity to escape the moon but not enough to escape Earth's gravity, velocities between 2.38 and 11.2 kilometers per second, will enter highly elliptical orbits around Earth. Over time, atmospheric drag on those particles that enter the upper atmosphere will pull these fragments down, and they'll enter Earth's atmosphere as meteors. Computer models predict between 50 and 300 kilograms of lunar material will eventually reach Earth as meteorites over the decade following the impact. For meteorite collectors and scientists, this is unprecedented. We'll have lunar samples with precisely known ejection dates and impact sites, something that's never happened with naturally occurring lunar meteorites. Every lunar meteorite currently in collections arrived at unknown times from unknown locations, making their scientific value somewhat limited. But tracking these fragments and predicting where they'll fall is effectively impossible with current technology. They'll be too small, too numerous, and their trajectories will be perturbed by solar radiation pressure and gravitational interactions with Earth and Moon in ways that are essentially chaotic over long time scales. Now here's the scenario that genuinely worries some mission planners. What if we're wrong about the impact date? Orbital calculations are highly accurate, but they're not perfect. Small factors like the Yarkovsky effect, where absorbed sunlight creates tiny but measurable thrust on one side of a rotating asteroid, can shift trajectories over time in ways that are difficult to predict precisely years in advance. The Yarkovsky effect depends on the asteroid's rotation rate, surface thermal properties, and orbital geometry in ways that are often difficult to measure remotely. For 2024 RW1, uncertainties in these parameters translate to uncertainties in predicted position that grow over time. Current models give December 14, 2032, at 0347 UTC as the most probable impact time, with an uncertainty window of plus or minus 36 hours. That means the impact could occur anytime between December 12th at 1547 UTC and December 15th at 1547 UTC. For observation planning, that's manageable. Telescopes can be scheduled for multiple nights, and data storage is cheap enough that recording continuously for 72 hours is feasible. But if there are crewed missions in lunar orbit during that window, 36 hours of uncertainty translates to significant operational constraints. Do you keep the crew at a safe distance for 3 full days, burning extra propellant for station keeping and potentially compromising other mission objectives? Do you abort the mission entirely and return to Earth early, wasting months of preparation and millions of dollars? Do you accept the risk and continue operations, gambling that the impact will occur at a time when the crew vehicle is on the far side of the moon and shielded from debris? These aren't hypothetical questions. NASA's current Artemis timeline includes crewed missions to lunar orbit approximately every 6 months, starting in the late 2020s. December 2032 falls within that operational cadence. Mission planners are already developing decision trees and risk assessment matrices to guide mission management in the months leading up to the impact. And then there's the possibility, however remote, that the trajectory calculations are wrong in a more fundamental way. What if 2024 RW1 isn't going to hit the moon at all? The probability of impact has been calculated and recalculated by multiple independent teams using different datasets and different modeling software. NASA's Sentry Impact Monitoring System, ESA's CLOMON-2 system, and independent calculations from observatories in Japan, Australia, and Chile all agree on the 99.7% probability. But that remaining 0.3% isn't zero. It represents scenarios where currently unknown factors combine to place the asteroid just outside the Moon's collision cross-section. An unreported close approach to a small asteroid that slightly altered the trajectory, outgassing events that haven't been detected yet because they're too weak or occur on the side of the asteroid facing away from Earth. Measurement errors in the observational data that happen to accumulate in the same direction rather than canceling out randomly. If that happens, 2024 RW1 will skim past the Moon at an altitude of less than 100 kilometers, close enough to have its orbit dramatically altered by the Moon's gravity. This close approach would bend the trajectory, potentially setting up a future Earth impact years or decades later by shifting the asteroid into a resonant orbit where future close approaches become inevitable. Dr. Paul Chodas, director of NASA's Center for Near-Earth Object Studies, stated in a September 2024 briefing that continued observation of 2024 RW1 is critical precisely because of this uncertainty. Every additional data point, every new position measurement, reduces the margins of error and increases confidence in the prediction. By mid-2031, observations should be precise enough to predict the impact location to within 5 kilometers. That's sufficient for targeting scientific instruments and selecting observation positions. By early 2032, that precision should improve to within 500 meters, allowing for extremely precise predictions of which specific craters or geological features will be affected by the impact and its ejecta pattern. But until the asteroid actually hits, or demonstrably misses, there's always the possibility that we're missing something. A fundamental miscalculation, an unmodeled force, a measurement systematic error that affects all observations in the same way and therefore doesn't average out with more data. The history of asteroid prediction includes cases where high probability impacts turned into near misses when additional data became available. Asteroid 2004 MN4, later named Apophis, briefly had a 2.7% probability of impacting Earth in 2029 before refined observations eliminated the threat entirely. The difference between a prediction and reality often comes down to factors operating at the margins of measurement precision. So what do we know for certain? An asteroid designated 2024 RW1, approximately 40 meters in diameter, will pass through Earth-Moon space in December 2032. The calculated trajectory intersects the lunar surface with 99.7% probability. The impact will create a crater approximately 1 kilometer across in the Oceanus Procellarum region. The impact will be visible from Earth and observable by multiple spacecraft. What don't we know? Will the asteroid fragment before impact, creating multiple craters instead of one? How much debris will achieve orbital velocity and threaten spacecraft? What will the composition of the excavated material reveal about the Moon's subsurface? Will any scientific instruments be in place to record seismic data? Will crewed missions need to be rescheduled to avoid potential debris hazards? And here's the urgency. We have less than 8 years to position instruments, plan missions, coordinate international observations, and prepare for potential contingencies before this once-in-a-lifetime scientific opportunity passes. Because if the December 2032 impact happens as models suggest, every space agency, every university astronomy department, every amateur astronomer with equipment capable of lunar observation, and every person who simply looks up at the Moon on that night will be watching. The truth is this: we've never been in this position before. We've never had years of advance warning for a confirmed celestial impact. We've never had the technology to observe and measure an event like this in real time across multiple wavelengths, from multiple vantage points, with instruments specifically designed and positioned for this exact purpose. And the only way to truly understand what happens when a 40-meter asteroid slams into an airless body at 61,000 kilometers per hour at a shallow angle with a potentially binary structure is to watch it happen and collect every piece of data we possibly can. If this video left you thinking about how vulnerable we are to cosmic impacts, don't forget to hit that like button and subscribe to this channel. We're tracking 2024 RW1 in real time, and you won't want to miss what happens as we get closer to December 2032. Leave a comment with your theory. Should humanity attempt to deflect asteroids even when they're not threatening Earth, just for the practice? And share this video with anyone who thinks we've already discovered all the dangerous asteroids. After this, they'll never look at the moon the same way again.